ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్
So, as part of understanding the entity, we will look at the different data modes that we can specify in the entity. Then we will specify and discuss the three different data types and what type of values that these data types can take. But before I start, I want to discuss a few key terms which we will be regularly using. First is the term assigned. If I have a variable or signal x and I have another variable or signal y, if I give the value from y to x, then typically I say that x is assigned the value of y. So please understand that. The second is read or reading a value. If x is getting the value of y, I say that x is reading the value. Or if y is getting it from z, then I say y is reading the value of z. So when you take a value, then it is typically called a read. When you give a value, then it is typically called a write. And then we have something called as a driver. A driver is a signal or port that gives a logic value as in 0 or 1 or a particular type of value, to a signal or a port. The person giving this value is typically called the driver. Person who gives the value is called the driver. I hope these three terms, we'll be using these three terms quite regularly. Hence I just thought that, I'll discuss these terms before we move on. So now, as part of knowing the entity a little better, we'll understand what are the different modes. We had seen previously that I had said that in the half adder, I had x and y or a and b of the type in. So on the other hand, I had sum and carry of the type out. This is what I meant, is that the mode needs to be specified, and mode indicates whether or not this particular port, that is A or B, can be read from the entity or not. So if it's of the type input, then yes, I can read from A and B, but if it's of the type output, I cannot read from sum and carry, but I can only write into it. So let's take a closer look at this. The signal also specifies, as I said, the direction of the driver. Like, what is the direction in which the person who is giving the value. So let's look at these in a little more detail. The most commonly used ones are in and out. This is less frequently used and this is least frequently used. Hence our focus as part of this course will be mostly understanding the mode in and mode out, and maybe a few times we will look at in out. So in the mode in, the example is fairly simple, that these are my keywords. Entity driver is, then I have the keyword port. I specify the pin or the port first. This is the mode of the type input, and this is the data type which we'll look at as a part of this lecture itself. Now that said, If it's of the type input or in, the driver or the person giving the signal is outside the entity. So only a person from the outside can give a value from this. The person sitting on the inside of the entity can only read. You can only read from the port, but you cannot write. Hence, this statement is the driver resides outside the entity. Hence, the person sitting on the inside or the signal sitting on the inside can only read from the port. I hope that is clear. Similarly, the type mode out, again, the syntax is fairly clear. The driver resides inside the entity. So the person sitting inside or the signal sitting inside can write the value to the output, but you cannot read the value. You cannot read the value from the output. You can only write the value, because again, it's an output port, so you can only write into the output port. You cannot read from the output port. Well, then your question is, when can I read from the output port? That is when I use the mode in-out. In-out typically means that you have the right to place a driver on the outside and on the inside. So, you can read the signal from inside and you can drive it from the outside. But I would like to let the viewer know that using an in-out type of port is a little tricky and not very straightforward. Hence, if you choose to model something like an in-out, I would suggest using an individual in and out, and then as a part of your architecture, you functionally make it of the type in-out. We will discuss that in a future lecture. So I hope that these three modes were clear. I have decided not to discuss the buffer type because it's a little more complex, and when you're starting out to learn VHDL, it's not really that important to know the buffer signal. Or the buffer mode, I'm sorry. So now, let's understand the data types. We saw in the previous lecture and in the current lecture that we have the mode or the port. This was the mode and this was the data type. So what I'm trying to say is, I have a port A which is of mode input and has the data type bit. What I'm trying to say is, or what VHDL says, is this input can take only the values which this data type covers, which is 0 and 1. So this port A cannot take any other values apart from 0 and 1. Fairly straightforward. Well, you must be wondering that if it's a digital circuit, I don't have any other values apart from 0 and 1, right? That's the question that must have come to your mind. Give me a couple of minutes and I'll answer that question. Boolean, on the other hand, has two values, true and false. So again, it is close to a programming language. Boolean is less frequently used, but nonetheless it is used. That if you have two states which is true and false, then you would use the type Boolean. The most commonly used is the STD or standard underscore logic. It is defined as a part of the standard underscore logic underscore 1164 package. Remember, in my previous lecture, I said that we could define our own package with our own data types. Similarly, the IEEE designed its own package, which is the standard underscore logic underscore 1164 package, which says that if I have a terminal A, which is of the type input or B of the type output, and I assign it a data type of standard underscore logic, then A or B can take all these 9 values, which is, it could be uninitialized, means I have not given it an initial value. It could be unknown, that in this point of time I don't know the value. It could be the traditional logic 0, it could be the traditional logic 1, it could be high impedance. I would like to spend 2 minutes discussing high impedance. Now, when you say that you have a logic 0, if it's a logic 0 at the output, that means that you are trying to take in current, that you are sinking current, and if the output is 1, you are sourcing current, means you are giving current. Again, this is in terms of current. When I say it's high impedance means that it is neither sourcing nor sinking. There is no current. There is no current, and that's what it means by high impedance. Don't care. And that said, the most commonly used values are these 3. U and X, uninitialized or unknown, is purely for simulation purpose. That is when you want to simulate your design and not actually implement it, just simulation, are these 3. U and X, uninitialized or unknown, is purely for simulation purpose. That is when you want to simulate your design and not actually implement it, just simulation. That's when you would look at uninitialized and unknown. So as you see that STD underscore logic covers the most realistic forms of values. Just want to quickly cover low logic 0 and low logic 1. A logic 0 means 0 volts. A logic 1 means high, for example 5 volts or maybe 3.3 volts. So a low logic 0 would mean something above 0 volts. So let's say 0.3 volts or 0.4 volts, not exactly 0 volts. And a low logic 1 would mean something like 4.5 volts or 4.2 volts with respect to 5 volts, or 3 volts or 2.8 volts with respect to 3.3 volts. So these are also realistic situations, but very rarely used. If you're using an FPGA, then you do have 0, 1 and high impedance. Time on the different styles of architectural modeling, which we saw in the first lecture, which were data flow, behavioral, and structural. We'll just spend a few minutes looking at each of these in a little more detail with an example. We did see an example in the first lecture, but as I said, that as a part of this entire lecture series, we will consistently see lots of examples. We will spend a complete lecture on the structural style, and we'll spend considerable time on the behavioral as well. So moving on. The architecture of a VHDL code or design, the major function of it is to specify the behavior of how my design will work or what my design will do, also how the outputs will vary with respect to my inputs. Obviously, the output is the function of the input. So the architecture typically specifies all these 3 points, that is the behavior, function, and relationship. We know that the syntax is architecture keyword, the architecture name, which is specified by you. The entity name must be the same as the entity of your design. Then we will have some declarations here like signals and variables, which we will see in a future lecture. And then we have some concurrent statements. Concurrent is that execute at the same time. They are all concurrent, so they execute at the same time. And we have the end keyword, which ends with the architecture name specified by you. So a few rules. The architecture can contain only concurrent statements. In a future lecture, we will discuss sequential statements, something that goes one after the other sequentially, but they have to be written in a special style, which we will discuss in a future lecture. But fundamentally, your architecture can contain only concurrent statements. The sequential statements will be written in a special style so that then they can execute as one process. And again, as I said, that will be a few lectures down the line. Now, the architecture can be specified using various levels of abstraction. What do I mean by various levels of abstraction is you can decide to show or specify the architecture at a gate level. If you have lots of gates connected to each other, you can describe it at gate level, or you can decide to describe it in terms of a behavior, that if you know how this complete circuit with function in terms of input and output, you can specify it in terms of behavior. So you can decide at what level of detail you would like to specify, whether it's at the behavioral level or at the gate level. It helps you design faster. It will give you a better understanding of how your design is if you define your levels of abstraction, and obviously lesser complexity, because the clearer you are with your design, the easier it is for you to design, and hence it is easier for you to implement. Now, a few more rules. One entity can have more than one architecture. As I said in the first lecture, you can have one entity which has multiple architectures, but you cannot have an architecture without an entity. Means you cannot tell the circuit what it's going to do without you knowing what are the inputs and outputs. So the different types of specifying the architecture body, or what goes inside the architecture. First is data flow. In the data flow style of modeling, you would use concurrent signal assignment statements. That is, if I have to specify an AND gate, I would just write C is assigns A and B. So A and B is assigned to C. If you want to make multiple gates, then you can say C is assigned A and B. You would say X is assigned Y or Z. So all of these statements will execute concurrently or in parallel. So this is the data flow style of modeling, where you specify how the data is flowing and from where. So how and from where. The behavioral style is a little more higher level. Reason being, let's look at the same example of an AND gate. For the time being, just ignore these keywords of process and end process and begin. Let's just try and understand this part. I will explain these terms of process in a future lecture. So if A is equal to 1 and B is equal to 1, then my C should be 1, else my C should be 0. So basically what I'm trying to say, I have a circuit which says that if A is 1 and B is 1, then my output C should be 1. Else in any other condition, for example, if A is 0 and B is 1, then my output is 0. Or A is 0, B is 0, output is 0. Or A is 1, B is 0, output is 0. Which in effect is what? It is an AND gate. But let's compare it to the previous situation. All I wrote here was C is assigned A and B, which was quite straightforward. Well, here you actually specified the behavior of your AND gate. Yes, it is a very long program for an AND gate, but as you see that when I will have to specify more complex digital circuits like multiplexers, then the behavioral style really helps me to model it correctly. Here we do not need to focus on gate level implementation. You don't really care about what the gate level implementation would be. Here you know it's an AND gate, but when you make larger circuits, when you are designing larger circuits, you do not worry about what my gate level will be. Well, then the question in your mind is, if I don't worry about the gate level, then who will? That's a very logical question that comes to your mind. The answer to that question is, when you write your VHDL program, you put it through something called as a compiler. A compiler is somebody who understands this VHDL language and then gives it to somebody called as a synthesis tool. Basically, what this synthesis tool does is, it looks at my VHDL code and says, okay, this is what you're trying to say. I am going to make an AND gate for you. So it is this synthesis tool who is a really smart person. Well, I'm just saying it's a person, but it's actually a software which understands based on your VHDL design what you are trying to say. So the synthesis tool actually takes care of converting your behavior or your high level description up to gate level. I hope that was clear. And your structural style, if you have designed, let's say, a half adder and you want to use a couple of half adders to design a full adder, so I would design one half adder which would have inputs X, Y and output Z for sum and M for carry. Then I would call the half adder 2 times here and here such that X, Y, Z, M, X, Y, Z, M, and I map the first X and Y to A and B. I map the second X to Z of the first full adder. I map the Y to the carry in. I map the output M, which was actually the carry of your half adder, to your OR gate, and then I OR the 2 carries. If I do this kind of design, then basically what I'm saying is I'm taking the structure of my design and putting it together. basically I'm just using some glue. So I'm taking these pieces, putting it together with some additional gates in between. Now the question is, I can choose to also make an OR gate and structurally use it here, and then it would be a completely structural style. We will see a detailed example. Actually, we'll see the same example of taking a full adder by making it using two half adders, and we'll see an example and a practical lab example. So I hope that the concept of structural was clear, just the concept. We will see a practical example soon. You can use a structural design to split a design into manageable units. So you can make small designs, combine them into one larger design, and then use this larger design to make one very big design. So this helps you manage your VHDL design into smaller parts. Another very important point that I would like to raise here is that a lot of the manufacturers of FPGAs, which we will be using as part of this course, they give you some predefined blocks. So let's say, for example, if you want to make a register, which is a storage element, you could write that in VHDL, but again, it's a very common thing. It's a blocks. So let's say, for example, if you want to make a register thing, it's a common known thing. So the FPGA, the vendor, basically vendor is the seller. The person who sells you the software already has the VHDL code for a register. You just need to call it in your design. So let's say if this is your design, then all you need to do is call the register VHDL code and you use it as a component, and thus you will use the structural style of design and save some time. So there are advantages to the structural style, but to be very clear, in your design that you will make as future designers,